It's really nice to be here. It's my first time visiting Monash, and it's an amazing department. There's so many people working on things of interest to me, so I'm really looking forward to chatting with all of you over the next week. So I'll be here through Friday. I work on a bunch of different things. Today I'm going to focus on massive stars, various topics in stellar evolution, binaries, supernovae. But I'd be happy to chat about other things like planets or white dwarfs or low mass stars or whatever you want to talk about while I'm here. The first thing I want to start with is the question of mass loss from red supergiant stars. So these are evolved massive stars that are, in most cases, burning helium in their cores. We know that they lose mass. This is very important for their evolution. We don't really understand how they lose mass. As far as I'm aware, there are not good models for exactly how that mass is lost. And the problem here is that we know that if you lift mass off the surface of a red supergiant, it will cool down, it will form dust. The dust becomes opaque to photons, and then the radiation pressure of the photons emitted from the red supergiant will drive away a dust-driven wind. The problem is that you need to lift material to several times the radius of the star in order for it to cool enough to form dust. So the question is, how do you lift that material off the surface of the star in the first place? That's the red supergiant wind launching problem, which is not solved as far as I'm aware. So I want to focus on this issue. To motivate this problem, there are nice empirical measurements and prescriptions of mass loss rates for red supergiants. So one example, this is Emma Beezer's paper from a few years ago, measuring mass loss rates from red supergiants in the Milky Way. So all of these stars here are in clusters where the mass of the red supergiants is approximately 10 solar masses. This is a different cluster where the mass is approximately 25 solar masses. You can see they lie on different relationships. So all these stars have about the same mass, and you see that there's a very strong relationship between luminosity and mass loss rate. You increase the luminosity by a factor of a few, and you increase the mass loss rate by 2 orders of magnitude. What you also notice is that this line for these more massive stars, it actually lies below this one. So that means at a fixed luminosity, if you increase the mass of your star, you actually decrease the mass loss rate by a lot. So this is important, right? It's giving us a hint as to how mass is being lost from these stars. And one of the important things to keep in mind is that at fixed luminosity, it's about a fixed radius for these stars. A more massive star has a larger binding energy, right? Deeper gravitational potential you have to escape. So that, I think, will be related to why we see this effect. There are other measurements of mass loss rates. This is a paper that came out just a couple weeks ago by Antoniadis, measuring mass loss rates for hundreds of stars in the LMC. And what they find is that above luminosities of about 3 times 10 to the 4 solar luminosities, we get this very strong relationship between luminosity and mass loss rate, similar to what we saw in the previous plot. Below that, at lower luminosities, there actually appears to be a kink and a flattening in the mass loss rates. And so this would be important for a theory to try to explain this, or at least explain either this regime or this regime. What I'm going to do is present a theory that maybe can explain this regime, probably cannot explain the low mass or the low luminosity regime. So what I'm going to talk about now is preliminary. It's work that I'm doing right now. It hasn't even been submitted or refereed or anything, so it's definitely still a work in progress, but I want to talk about it because I think it's interesting, and I'd be welcome to get your feedback. The basic idea here is that red supergiants have these very turbulent surfaces where the convective motions near the surface of the star are about the sound speed of the star. And this means that you will launch acoustic waves that go out into the material above the star, and very quickly as the density goes down, those acoustic waves will steepen into shock waves that then go out through the chromosphere. And those shock waves deposit energy in this chromosphere. They also deposit momentum, and that's going to be important for understanding how much mass we actually have in this chromosphere around a red supergiant. An important thing about these chromospheres, as we'll see, is they're quite dense. What I mean by dense here is that the cooling times due to various molecular emission processes are quite fast. So this is different from the sun's corona. The sun's corona is very hot because it can't cool, because it's very low density. We'll see that these are in a high density regime where cooling is very effective. That means if we heat up this gas, it actually cools down back to its equilibrium temperature quite quickly. So the energy deposited by these shock waves, or the heating they produce, is probably mostly just going to be re-radiated, but the momentum will help drive material off the surface of the star. And I think that's going to be the important effect. So this idea is not new. Some people have looked at this in the past in the context of things like AGB stars, Myra variables. This is a paper by Bert Schinger and Chevalier from a few decades ago. And this is just a simple model for, they have this train of shock waves. So this is a train of shock waves going out into the material above the star. And this is the density profile. So you get these sudden jumps at the shock front. But on average, the density is basically falling exponentially on this effective scale height. And that effective scale height is determined by the actual velocity of these shock waves. This is temperature. So what you see is you increase the temperature right at the shock front, but then you quickly cool back down to this equilibrium value. And so this is, I think, the basic picture for what's happening inside of the chromospheres of these stars. And what you get from a model like this, if you assume that what is holding up the material in this chromosphere is basically the momentum due to these shock waves, you can solve for what the density profile is. So we're basically calculating an effective hydrostatic equilibrium where we have gravity pulling stuff down, and then you have the momentum deposited by waves supporting things. And the waves have this characteristic velocity v turb, which on this plot would be basically the amplitude of these velocity jumps. And that's actually a constant in these models. They showed that, at least for a solution with a steady train of waves, that's roughly a constant. So then you get that the density profile basically falls exponentially as you move away from the surface of the star. So this is very similar to the density profile you get if you assume an isothermal atmosphere, which is, a good simple model for the atmosphere above the sun, except instead of the sound speed being the relevant velocity, it's this shock speed or this turbulent speed being the relevant speed. And that can be, in principle, can be larger than the sound speed. So we can actually make the density fall off slower. It turns out for the velocities we expect, in most cases, that is not enough to get a lot of mass into the chromosphere. But an important consideration is that, these stars have these very vigorous convective motions, and those motions are not, they're stochastic, they're varying. So there's some spectrum of turbulent convective velocities. So there's going to be some spectrum of shock wave velocities going into the chromosphere. So what I'm doing right here is just assuming a very simple spectrum for what those velocity, for the probability of those velocities. I'm just assuming it's a Gaussian velocity distribution, where the typical velocity is the convective velocities at the surface of the star. This is about what you expect for Kolmogorov turbulence. Turbulence in these stars may not actually be Kolmogorov, but I think it's a reasonable starting point. So if you have this probability distribution of turbulent velocities, you can calculate an average density profile inside the chromosphere of the red supergiant by basically averaging or taking the integral over this velocity distribution. So then you get this nasty integral. Turns out that this simplifies into this expression. So in other words, the density as a function of radius, it falls off as 1 over r squared plus this exponential term, which goes like the escape velocity divided by the convective velocity. And typically that's about a factor of 10 in red supergiant. So what this means is we get this 1 over r squared effect, but then we also get an e to the minus 10 roughly is what comes out here. So these are some plots showing what those density profiles look like. So for a given, if we imagine that turbulent velocity just was about 0.08 the escape speed, which is about typical for red supergiants, then the density would fall off very quickly. But there will be these kind of uncommon moments where the velocities are maybe a few times larger, and then the density profile falls off much more gradually. And the time average density profile in this model is the black line. So what you can see here is that this typical density in the chromosphere of the red supergiant, it actually, I mean, it does fall by several orders of magnitude as we go away from the surface, but it's actually much larger than you might naively expect from simple models of mass loss. So for instance, this yellow dashed line, this is what the density should be if we had a wind coming off the red supergiant with a constant velocity of about 30 kilometers per second, which is a typical wind speed for a red supergiant. If you just extrapolated the wind from large distances all the way to the surface of the star, you'd get densities near the surface of the star, see at 2 times the radius of the star, you'd predict a density of about 10 to the minus 16, whereas in this model, the actual density should be a few orders of magnitude larger. And this is important because when people observe supernova coming from exploding red supergiants, they're often using these models for what they expect the material around the star to look like. And so this model, this will come into play later, is predicting much larger densities. The other thing that's important is, so this density is falling off rapidly. At some point, you start forming dust, and that depends on the temperature profile. But typically, we expect to start forming dust several times the radius of the star. And so based on the density there, you can figure out what the mass loss rate of this chromosphere should be, is basically the area at that dust formation radius times the density times the outflow velocity, which should be about the sonic velocity there, or in this case, the convective velocity. And so this works out to a mass loss, this very simple expression for mass loss rate that goes like this. And again, we get this factor of e to the minus v escape over v con, which is about a factor of 10. So if you calculate this mass loss rate for realistic models, so now I make MESA models of stars where I'm calculating the surface density, the convective velocities at the surface of those stars, the escape speeds. Then I use this expression for the mass loss rate. What I get is these colored points here. So this is mass loss rate of an evolving 12 solar mass star. So each triangle is at a different point in the evolution of a 12 solar mass star. Here's a 15 solar mass star. And you can see that these predictions for mass loss rate roughly follow this observed distribution above this kink in the observed mass loss rate. So it can match this kind of steep distribution of mass loss rates up here pretty well. What it can't match is these very low luminosity red supergiants. We're under-predicting the mass loss rates there. So I would guess that there's some other mass loss mechanism that becomes more important down here, maybe related to Alphen waves or magnetic activity. That's what drives mass loss in low mass stars like the sun. But maybe we can explain these high mass loss rates for these stars. Another interesting thing is it predicts very large mass loss rates, 10 to the minus 5 or 10 to the minus 4, for 30 or 40 solar mass red supergiants. You can see there's only a few points on this plot. What happens in these models is they lose their envelope so fast that very quickly they basically lose all their envelope and they turn into yellow supergiants. And then this model doesn't work so well. So it might explain why we don't see red supergiants at these luminosities, because they just very quickly lose all their mass. Another interesting thing is these stars here, this is the mass loss rate right before the star goes supernova, according to this model. And you can see it can be an order of magnitude or two larger than when the star was burning helium in its core, which is kind of down here. What happens is these stars expand. They get a little brighter right before they explode. That means their radius gets larger. And so their escape speed gets a little bit smaller. And that increases their mass loss rate. So it predicts higher mass loss rates right before the supernova of order 10 to the minus 6, or a few times 10 to the minus 5 or so. Yeah.
So there's still one parameter here in this model, which is the dust formation radius, which probably depends on the periodicity.
That's right, yeah. So I'm using very simple assumptions about the temperature. I'm assuming it basically falls off as r to the minus 1/2, which is about what you expect for a gas that's in equilibrium with the radiation from the star. The dust formation radius ends up the models aren't very sensitive to that as long as it's much larger than the radius of the star, right? Because as long as RD is a large number, then this number in the square root goes to 1. And so then it doesn't appear anywhere in this expression.
So, for example, if you had a star, but this goes to 0, there's no dust.
Yes. Yeah. I haven't accounted for that. So I think you're right that if you're at very low metallicity, you wouldn't form dust, and then it's not clear how you drive mass, all the way to infinity. So the model would probably break down for very low metallicity. Will it still work for LMC? My guess is yes. The metallicity is not that low, but where it starts to break down, at what metallicity this would break down, that's an open question. Again, this is preliminary, so there's lots of things I don't understand yet. Yeah.
Sorry, I think I missed the critical step of how the luminosity is connected to the convective velocity.
So if you have higher luminosity, you have higher luminosity, right? Because the flux is something like 4 pi rho r squared convective velocity cubed, approximately. So higher luminosity tends to mean higher convective velocity. It also means usually larger radius for these stars, which means smaller escape speed. So both those things tend to mean higher luminosity translates into much larger mass loss rates. So you can compare these models to empirical prescriptions. So these ones are the ones from Beezer's paper. A simple Reimer's mass loss model is these black ones. The de Jager ones people sometimes use in models are these light gray diamonds. So the main thing is that this model predicts a steeper scaling with luminosity than some of the others. It's about the same typical values for your prototypical 15 or 20 solar mass red supergiant, but it predicts more mass loss for more luminous, more massive stars, and less mass loss for less luminous red supergiants. So that's the prediction that, to first order, it's consistent with these stars, but this is something we'll have to look into in more detail. So I said the other interesting thing is now we have all this mass above the chromosphere. It's typically of order 100th of a solar mass in these models. When the star is a normal star, this material has very low opacity. So it's basically transparent. It wouldn't affect what you see from the star too much. But once the star explodes as a supernova, we have this very high energy shock that goes out, releases a huge burst of ionizing radiation, and will ionize this material. And once you ionize it, now you have electron scattering opacity, and so you get a much larger optical depth. So this is the optical depth for the same density profile as I showed you before, once you ionize this material. And you can see that this chromosphere can be optically it can be optically thick out to 2 stellar radii or something. So this is going to have potentially an important impact on what the light curve of the supernova looks like in the early phases of evolution, when the photosphere of the supernova is, within a few stellar radii. So that's the first few days after the supernova. We have some very preliminary models, but this is actually slightly older models. These colored curves are just SNEC models for the light curve when we explode these stars. The main thing I want to point out here is if we have no chromosphere on top of the star, we get this very narrow, sharp peak at shock breakout. That's this peak. And then you have the plateau of the supernova after that. As we ramp up the mass in the corona, we go from blue to green lines. And then this peak gets broadened, and we have this phase of kind of cooling as we settle onto the plateau. And we're seeing that in a lot of type 2p supernovae. The green points are 2023 IXF, which is a supernova that just recently exploded, very, very well monitored. So we can't actually match this light curve yet. And there's various effects that may come into play there. But it goes in the right direction. I think this will be very important, not just for matching the light curves, but for matching the spectra of supernova. There's many of these type 2p supernovae in the first week or so after the explosion we see flash ionized emission lines in their spectra. And that must come from some material around the star that's been ionized by the supernova shock breakout or subsequent photons coming from the shock front, and is then recombining. And when you recombine, you get those emission lines. So I think this is a promising way to explain some of what we see there. And also just understanding red supergiant mass loss rate. So like I said, in this model, stars more than about 25 solar masses, they lose all their hydrogen during the helium burning phase, and then they should turn into helium stars or Wolf-Rayet stars. Whereas the low mass red supergiants in this model, they lose essentially no mass. And all of this can potentially happen in low mass stars too, stars at the tip of the red giant branch or the AGB phase. The same process could act in those stars. So that's something I'd like to explore in the future. Okay, so now we're going to transition. So we did hydrogen-rich stars. Now we're going to talk about helium-rich stars. This is some work my student Samantha did. And what we're focusing on here is these are helium stars with masses of 2 to 4 solar masses, roughly. So they descended from main sequence stars of 10 or 15 solar masses, something like that. But we know that lots of massive stars are in binaries, and a lot of the time that hydrogen envelope gets stripped by a binary companion. And so you're left with a helium star orbited by a binary companion. And what's interesting is these helium stars, if they're less than about 4 solar masses, at the end of their lives, they expand enormously. So similar to low mass stars going up the red giant branch, these helium stars can expand from 1 solar radius to 100 solar radii at the end of their lives. And that means they can start interacting with this companion again near the end of their lives. And that produces a phase of mass transfer called case BB mass transfer, where this helium envelope now starts getting stripped off of the star. And so this phase of evolution is well known to people doing models of binaries, binary models of massive stars. Basically what we did was take this process all the way towards core collapse. So this process will keep going on. And what we found is that it intensifies greatly in the final years of the star's life. So these are some of Samantha's models. These are just single star models right here, showing the radius of these helium stars with the range of masses from 2.5 to 3 solar masses. So what you see is they all start expanding about 10 to the 5 years before core collapse. That happens when you go from helium core burning to helium shell burning. The squares here is when we start carbon burning in these models. You can see these stars expand by a factor of like 200. So they expand enormously. That's what drives case BB mass transfer. What you can also see is if you keep evolving these models, they often shrink a little bit, maybe 10 years before core collapse or so. That's associated with neon ignition, which actually decreases the helium burning luminosity and causes the shells to contract, the helium envelopes to contract a little. But then they inflate again at the end of their lives, potentially by a factor of a few. And this late stage inflation, this is super important because it means these stars are now expanding. Right here, they're expanding on a time scale of 10 to the 5 years or so. Here, they're expanding on a time scale of 1 year or a month or something. And that means that they'll start mass transfer again, and now they'll start mass transfer at an enormous rate because they're overfilling their Roche lobes really quickly. So these are binary models. These are binaries, in this case, at 100-day orbital period and 10-day orbital period. So this is the mass loss rate in these models. So right here is the ordinary case BB mass transfer, mass loss rates of order 10 to the minus 4 solar masses per year. This late stage mass transfer can be a factor of 1,000 larger in the mass loss rate.
There's synchronously rotating?
Yeah. Yep. So we're just assuming it fills the Roche lobe and is tidally synchronized.
But this fast expansion,
Yeah.
has it got time to do that?
Good question. Yeah. That could change these mass loss rates a little, I suppose. I think regardless of whether or not it's synchronously rotating, it's going to keep expanding until it overflows its Roche-lobe. So you're right that the
But the angular momentum, like it's carried away or it's accreted.
yeah. So what happens to the mass after it's lost is very unclear. We're not modeling that explicitly here. We're basically assuming it's lost from the system. But it, and I'll talk about this in a second, it is unclear what happens to it. I think it's inevitable you get very large mass loss rates in this stage. At 10-day orbital periods here, what actually is happening is these models are going up and then they're crashing. And anybody who's run MESA knows that it crashes sometimes and you don't know what's going on. We think either the mass transfer is going unstable or it's just getting hard for the models to converge. So what we do here is just assume the mass loss rate continues afterwards at a steady rate. But really, probably the mass loss rate keeps going up. So the total amount of mass you can lose from these stars in the last year of evolution or so can be of order 1/10 of a solar mass. And again, maybe for these ones it's a little bit less, but these are probably lower limits. So these stars can lose a huge amount of mass in the final year or so of their lives. And that means that mass won't have gone very far by the time these stars explode. So here's some models. Here's how much mass our models lose in this late stage mass loss as a function of the helium star mass. You can see it's anywhere from 10 to the minus 3 to 10 to the minus, a few tenths of a solar mass. The radius out to which this material expands is not clear. So there's no way that the accretor can actually accrete all this mass so quickly. Probably what happens is this mass is lost into some sort of circumbinary torus. It's not really clear what happens during that phase. To do this calculation, what we assume is that the mass outflow is at about the orbital speed of the binary. That's kind of the characteristic speed at which we expect an outflow. Then we expect that mass to expand out to radii anywhere from about 1 AU to 1,000 AU in the time before the star explodes. So we expect of order 1/100th of a solar mass, extending out to radii anywhere from a few to hundreds of AU when the supernova goes off. And that's right in the sweet spot such that when the supernova ejecta hit this mass, they hit it, within a few days after exploding. It's going to have a huge effect on what the supernova looks like. This right panel, we're doing the same thing, but now we're assuming that the mass transfer goes unstable. So we basically assume you have a little common envelope event. And then in that case, you would basically eject the whole helium envelope mass, which is typically a few tenths of a solar mass in this case. And what's interesting actually is if you use an alpha prescription for the common envelope that would happen, you can estimate what the orbital period would be after that. And it can be anywhere from hours to minutes, which could give you actually very short neutron star merger times if the secondary is also a neutron star. So this might be a channel to make very prompt neutron star mergers, which has some interesting applications. But I won't say anything more about that right now. What I will say is I think this is a promising channel to make some of the weird type 1b, type 1bn, ultra-stripped supernovae, all these kinds of interesting supernova observers are finding. What I'm plotting here is, again, the estimated radius and mass of the CSM ejected through this process. And the colored points with uncertainties here, these are observed supernovae, where observers have tried to estimate the CSM mass and radius based on modeling the light curves and spectra. And all these points over here, these are type 1bn supernovae. These are supernovae where we see no hydrogen in the spectrum. We see helium, but instead of the normal helium absorption or P Cygni profiles, we actually see narrow helium emission lines, which is an indicator that we have a helium-rich CSM that the supernova is crashing into and creating emission lines. So we think this is pretty promising channel for these 1bn, where these events over here, these are ultra-stripped supernovae where people also see some evidence for some CSM. So we might be able to explain some of those events as well. We haven't done any spectral modeling of these, so it's a little unclear. We are working on some light curve modeling, and we can match some of these types of events. I'll just say a little bit about that briefly. There's a student at Caltech, Gustav Das, who's been finding some weird type 1b supernovae. So for example, this is a double peak supernova where we have an initial rise and fall, and then this is the main part of the light curve, which presumably is like an ordinary 1b supernova. But then we have this initial peak here, which is sometimes very prominent or sometimes less prominent in these events. But this early peak in the light curve is an indication of some sort of CSM or extended envelope of these stars. And we think that this process is one way that you can make that. So there's some more on this. I'm not going to go into it, but I'm happy to talk to any of you about the supernova coming from these events. I did want to get to the last topic, which is related to angular momentum transport and the spins that we expect to find inside of stars. This is basically an unsolved problem, or it's a problem we're making progress on, but we still don't totally understand. The issue here is that as stars evolve, their cores typically contract and their envelopes typically expand. And that means if those layers of the star conserve their angular momentum, you'd expect a core to spin up and be rotating much faster than the surface, which has expanded and spun down. Okay, but as soon as you have differential rotation, you're going to start having frictional processes inside of the star that might try to transport angular momentum, even out that rotation such that we bring this star closer to rigid rotation. And one of the really important developments here is not from high mass stars, it's from low mass stars, where we're starting to get amazing data that provides very strong constraints on what's going on. So the most useful systems have actually been ordinary, like 1 to 2 solar mass red giants, kind of at the base of the red giant branch. The reason is that these stars pulsate. First of all, they're very common. Second of all, they pulsate at low amplitudes, and that's been measured for thousands of red giants by the Kepler satellite and now the TESS satellite. And so what they do is they just observe the luminosity of these stars, then you take a Fourier transform of that, and you see peaks in the power spectrum. Each of these peaks is one of the oscillation modes of the star. And the most useful oscillation modes are these groups. These are triplets. You see they have 3 modes here, 3 modes here. These are L=1 spherical harmonic. That's the angular structure of these modes. They're split into triplets because we have M=-1, 0, and 1 oscillation modes associated with them. And they get split in frequency due to the rotation of the star. So the M=1 mode is propagating around the equator of the star the same direction as the rotation. So it gets shifted to higher frequency by the rotation. The M=-1 gets shifted to lower frequency. So if we measure the splitting, we can measure the rotation rate of the star. But what's really interesting here is these modes, especially this one, these are modes that go all the way into the core of the star and back out. So this measurement is not a measurement of the surface rotation, it's actually a measurement of the core rotation rate. In fact, the signal is dominated by the core of the star. So we can actually measure core rotation rates for many stars. And I'll show those measurements in a second. So the question is, what are the angular momentum transport mechanisms that try to slow down the spin of the core? And is that compatible with what we see? So an important issue here are magnetic fields. The reason is, as soon as we have any differential rotation inside of our star, even a weak magnetic field will get amplified. So this is actually just the magnetic induction equation here that tells you how fast the toroidal component of the magnetic field increases as the radial component of the magnetic field gets wound up by differential rotation. This is a simulation of that process that just shows even a weak magnetic field gets wound up by differential rotation into these toroidal loops. And once you have a strong toroidal field, it can become unstable. And we think the first instability you encounter is something called the Taylor instability. Basically, if you have a very strong toroidal field, it becomes unstable. And what happens is these loops of magnetic field actually slip sideways. So this is something that Hank Pruitt worked on a few decades ago. And so this instability is called the Taylor instability. And the question is, how does that instability saturate? What's the outcome of that? That's the problem we don't know how to solve yet. So what we can start to do is do simulations of this process. So this is a simulation done by Swoching Ji, who was at Caltech, of the Taylor instability. It's actually a 3D simulation. I won't go into all the details here, but basically what we're seeing in this simulation is, you see here these loops slip sideways. That's basically the different colors here are loops slipping sideways with respect to each other. So we're starting to do simulations to understand the nonlinear outcome of this instability. I'd be happy to talk about that. We don't totally have the answer, largely because we can't actually run these simulations for realistic parameters that we expect inside of stars. But what I have done is try to develop some models, some simple models for the outcome of this instability. So these are very similar to the models that Hank Sprout developed, which became the Taylor-Spirit dynamo, which many of you may have heard about, often put into stellar evolution codes. So this is a very similar idea here. It's just we have different arguments about how this instability saturates. The basic idea is that you have a growth rate, a linear growth rate, and we're setting it equal to some nonlinear damping rate. And then we're basically using energy conservation to figure out how much the fields actually get amplified. So what we're doing here is we're setting the energy input into the magnetic field by differential rotation equal to what we're estimating as the energy dissipation rate due to this instability, which is causing turbulence and dissipating energy. So at the end of the day, we get an estimate. If we combine these equations, we solve for the radial and toroidal components of the magnetic field. Those give us a Maxwell stress, which transports angular momentum inside of the star. We can write that as an effective viscosity that's reducing the differential rotation of the star. And it goes like this. It goes like the rotation rate divided by the buoyancy inside of the star squared. The important thing here is that we think this exponent is 2, whereas in the Taylor-Spirit dynamo it's 4, basically. And because this number is a small number, we predict more angular momentum transport than the classic Taylor-Spirit dynamo. And this, if we incorporate that model into a stellar evolution model, we get closer to explaining the data. I'm not saying we're going to do it perfectly, but what I'm plotting here is just a model of a 1.6 solar mass star evolving in time. The red line is the rotation rate of the core in this model. The blue line is the rotation rate of the surface. The star is basically rigidly rotating until the start of the end of the main sequence is right here. Red giant branch starts about right here, and that's about where the core decouples from the envelope in these models and begins to rotate much faster. And so this model predicts core rotation periods of order 10 or 20 days at the base of the red giant branch, which is about the typical measurements that have come out of asteroseismology. So there's a lot of scatter in the measurements, but they're typically of this order of magnitude. The Taylor-Spirit dynamo predicts about a factor of 10 or 20 faster rotation, predicts rotation periods less than a day, which is too fast to explain the data we have. And then these models keep going. Basically, we maintain that. So the Taylor-Spirit dynamo also predicts too fast rotation for the cores of clump stars. These are helium-burning stars, and for white dwarfs. This new model gets closer to matching the data, although there are some issues that can't match everything we see, which I won't get into right now. But it gets closer to the data.
So why is the initial rotation different between tracking?
I think it's because I'm just plotting the core rotation rate, and I think these Taylor-Spirit models aren't actually rigidly rotating right at the end of the main sequence here. They're close, but not quite, I think. Okay, so this gets closer to matching what we see for low mass stars. So the question is, what does this imply for high mass stars? So we basically put the same model into models of high mass stars. And this plot is showing the angular momentum contained in the core of massive stars from 10 to 40 solar masses as they evolve. What's happening here is this is the main sequence evolution of the star. The core has a large angular momentum. But after the main sequence, the angular momentum in the core is depleted by about 99% due to this process. The reason is the core is trying to contract and spin up, but it's coupled to the envelope by these magnetic fields, and so it's losing its angular momentum to the envelope. So that's what's happening. And so by the end of the star's life, the core has lost most of its angular momentum. This predicts neutron stars. If we take the angular momentum at the very end of the star's life, it predicts neutron star rotation rates of order 100 milliseconds, which is about right, maybe a factor of 2 too slow or something, but it's not too far off from what is inferred for young pulsars. And we can do the same calculation for progenitors of black holes. And what I'm plotting here is the spin that we expect of black holes as a function of essentially the mass of the black hole. We're assuming here that everything that's in the helium core of the star falls into the black hole and everything that's in the hydrogen envelope is ejected, which probably isn't perfect, but is about what we expect. And you can see these black models are models of single stars, and according to this model, they're always slowly rotating. Their dimensionless spins are of order 0.01 or a few hundredths or something. Now, to first order, that's consistent with what we see in LIGO data of merging black holes. There, for individual events, the uncertainties are quite large, but most of these events, what we can measure is this effect chi-f. Of course, lots of people here know this. So these are often have big uncertainties, but are often consistent with zero. There are some events that are inconsistent with zero, so those can't easily be explained by this simple model. What these green and yellow points are different kinds of models of massive stars. This green point is a model where during the helium burning phase of a massive star, we do some tidal spin up that rejuvenates the angular momentum of the core and gives us a more rapidly rotating black hole. This yellow point is a model of homogeneous evolution, where basically the star never develops a hydrogen envelope because it remains fully mixed. And that allows it to conserve its angular momentum. So I'll go through this quickly, but with my student Linhao, we've also looked at the tidal spin up that we expect. So here what we have is we're looking at the problem where we have a black hole and a helium star. Before the helium star collapses into the second black hole that will then merge, the question is, can it get tidally spun up such that it is rapidly rotating and creates a rapidly rotating black hole? So the prescription people have used is the Zahn model. This is a classic model from the 70s. So I've used that in some models. I'm going to skip through these since we're short on time. What Linhao has done is actually take a more detailed look at what this tidal spin up with some sophisticated models where he's calculating stellar structures, calculating oscillation modes, calculating the extent to which they're excited by tidal forces, and how much angular momentum they deposit inside of the star. That's what the black line shows here. You can see it's not the same as the yellow line, which is the Zahn model that most people use. So unfortunately, reality is a bit more complicated. It's a pretty good approximation in some cases, but pretty bad in other cases. I'll just skip to the results. The net result is we tend to get a little bit less tidal spin up from this when we do this calculation this way compared to the simple prescription. What this plot is showing is the spins we expect for these black holes as a function of black hole mass. And this is a very busy plot, so I apologize, but the different colors are different orbital periods. And the thing to take away here is that the green models, which are at long orbital periods, they basically have no tidal spin up. So you get a low spin of the black hole in those cases. The red models are black holes at short orbital periods. There, the tidal spin up is pretty efficient. And so we can get high spins in those cases. We actually get a little higher spin for our low mass black holes than our high mass black holes, which is interesting. And one of the things we try to understand is, do we see this in LIGO? Can this be consistent with what people are measuring with LIGO? So I know the group here has done a lot of work on this. This is one of plot from one of Christian's papers. It seems there's this pretty robust correlation between the mass ratio of merging black holes and the chi-Fs, where lower mass ratios appear to be rotating more quickly. We haven't tried to explain that yet. The other thing that I think this is less secure is there could be a correlation between mass and spin in these events. And so one of the things we'd like to do in the future is actually create populations of these systems and try to understand if we can predict any of these correlations that can then be observed. So we haven't done that yet. We've just done the detailed calculations for individual models. What we'd like to do is do this for a whole population of stars so that we can actually predict whether or not there are these correlations. So I will leave it at that and take questions. Thanks.
So going back to your red supergiant mass loss stuff, is that assuming spherical symmetry?
Yep, it's a simple model, spherically symmetric. In reality, it won't be spherically symmetric. You'll have, stuff.
All the observations have like collimated jets and all this other asymmetric rubbish for like galactic red supergiants.
Yeah, so I think the picture that I'd like to advance is something like what we see in this picture here, which I made with Dolly 2.0, I think. But it's, there's blobs rising off one side of the star, falling back on the other side of the star. So I don't expect it to be spherically symmetric at a given time, but on average, I don't expect a preference in any one direction.
And that's not really what the observations show.
What do you mean?
Highly asymmetric. We have like very collimated jets. We have the great dimming of Betelgeuse. Like
Yeah, so
it's not like roughly symmetric like an AGB star. The red supergiant is much more.
I'd like to talk about collimated jets from red supergiants. I'm not aware of that. But from Betelgeuse, yeah, I understand there's this great dimming event, which was kind of on one side of the star. And that is sort of what I expect from this, is you might have sort of an epoch of convective activity at one side of the star, which ejects mass from that side of the star, but not from the other side of the star. So at a given moment in time, it could be very asymmetric. But maybe we should talk more about that.
I have a question, yeah. So you showed your models where you said the models actually crash just before silicon burning. So one question was, how do you know you're, days away from the onset of silicon burning if the models crash?
Yeah, we know where they are when they crash, right? And we can compare to like single star models that aren't doing this mass transfer process. So it's true that we don't know exactly what this time scale is before silicon burning, but we know pretty close.
And my other question was, do you know the dynamical timescale of your donor star here? Is that...
Yeah, so that'll be a function of its radius. So basically what's happening is they're filling the Roche lobes. They're actually overfilling the Roche lobes. Some of these mass loss rates up here are actually pretty questionable because they're overfilling the Roche lobes by 50% or something. So, but it is going to be a huge mass loss rate. So the dynamical times for these things, my guess is that they're of order weeks, although I'd have to look up the number. These things are something like 100 stellar radii. Whereas here, these are more compact binaries, so it's going to be a shorter dynamical time, maybe hours. Yeah, so there's a range. So it is shorter than the evolution time, although actually at the very end, they're starting to get comparable.
Yeah, exactly. So then the point is the stars sort of falling apart anyway, so your models wouldn't be able to converge if you assume hydrostatic.
That's right. Yeah. So at the very end stage, they're starting to get out of hydrostatic equilibrium. Yeah.
Any other questions?
How secure is that? You said that relationship between mass ratio and effective spin is quite secure. Can you expand on that a little bit?
My understanding is it's not secure. Mass ratio and effective spin. My understanding from this group's work, from stuff that Eric and Paul and Christian.
I heard you and you didn't say it was secure.
I think there are a couple groups that have claimed a fairly secure relationship, just saying that there is a correlation between mass ratio and spin. That's my understanding, but If anybody knows better, but you can correct me.
I think it's like a log base factor of 4 or 5 for every correlation. So it's decent, like moderate evidence, yeah.
Yeah, and I think that's been found by a couple groups. So, well, the next observing round should tell us, I think. But anyway, that one looks somewhat secure. I've heard people say they don't believe this one. So.
Yeah, a follow-up question on that, because I think here you have this like line of zero spin and you also have the scatter. So I mean, maybe to me it seems like you have some isolated binary channel and a dynamical spread over a little bit. So how can you show that the spin you have at the end of the evolution is actually the spin you measure at the merger? There's maybe some stuff happening between.
So from the models, yeah, basically we calculate the angular momentum in the star at the moment of core collapse and just assume everything falls into the black hole. So we're doing the very simple thing. It's true that there may be more complicated effects, right? You may actually get a partial explosion during collapse to a black hole, and you may eject some material, and that may affect the spin of the black hole you get. So we're not accounting for any of that. As for what's going on in this plot, I'm not qualified to answer that question. I think you have some population model, I think.
Yeah, there's a population that basically takes everything that's sort of negligibly spinning, so like not measurably rotating, and then just models the correlation between the things that you can meant to be spinning. So it gets a little bit complicated, but I'll chat more later.
I guess 2 quick comments / questions. So one was when you mentioned that dynamically unstable case between mass transfer leading to common envelopes. So Alejandro Vini Gomez, when it was like using in Birmingham like 5 or 6 years ago, wrote a paper where he pointed out that at least it couldn't be too common that they would go through a common envelope, because if they did, we wouldn't be able to reproduce the galactic neutron star systems. The galactic neutron star systems have not gone through a common envelope. Although they're quite short, a second common envelope following case to be mass transfer, because of, their orbital periods are few hours to few days, right? And that's they would end up being too compact if they went through another common envelope following case to be mass transfer. Although of course some of them could have done this, right?
Yeah.
And they just wouldn't appear in the galactic population. They're too short-lived, then they would still appear in the area.
Yeah, so that may suggest that usually it stays stable. Also, all of this is only happening in a fairly narrow mass range, so it certainly could be other mass ranges that are dominating the population. So yes, I don't expect this to be extremely common, but it is interesting that maybe it could produce a channel of very rapidly merging neutron stars.
And then the other sort of kind of question is, so you showed some fairly massive black holes, at least if you, I think, assume the classical tidal models that have maximum spin. Pablo Marchand argued recently that above a certain black hole mass, you can never reach maximum spin, and the argument is essentially that your Wolf-Rayet stars at this point are so luminous that they're actually the Eddington luminosity is well, you're operating at non-negligible pressure Eddington luminosity, which means you have a reduced effective gravity, and that means that your maximum rotation rate is actually much lower than the nominal Keplerian rotation rate. So regardless of how much you spun up the star previously, you can spin itself down
Through mass loss.
through presumably through mass loss, but it would have to somehow spin itself down.
So these things, at least our models, when they're in this helium burning phase, they're not spinning very rapidly. So I'd expect that to not be super important, although it is true that these results depend on what we assume about mass loss rate during that phase. So we're using, I think, the Dutch prescription for mass loss in MESA. And so if the stars actually lose more mass than that prescription, these spins would be lower. And if they lose less mass, then they could be a little higher. So there is definitely uncertainty there.